The Central Limit Theorem. What does it say? What does it mean? And why is it so freaking important? If you stick around to the end, you're going to find out the answer to all three of those. Hey guys, and welcome back. My name is MrCaproni, and this is Probability and Statistics. Today we're going to be covering the Central Limit Theorem. Now, this is an awesome tool used alongside with sampling distribution to go ahead and help us apply some of our predictions and probabilities to general populations when normally we wouldn't be able to. In this video, we're going to talk about what the Central Limit Theorem says, kind of break down what that means, and then talk about how we can use it. So I hope you learned something new and stick with me all the way to the end. See you there. Let's go ahead and dive right in. So I hope you saw my last video on sampling distributions because it kind of sets the stage for our discussion on Central Limit Theorem today. If not, you can actually find it in the link above. Now, if you did, then the super short version to wrap up was the fact that when we're taking sampling distributions, we're essentially taking a sample over and over again from a population and then recording some type of summary statistic like the mean of those samples. Then we create a whole new distribution based off of those. And an interesting thing that came out of that is that the mean ends up being the same for the sampling distribution, but the standard deviation ends up getting a bit smaller. We'll talk about all the reasons why in that video, so make sure you check that out so you understand that before we dive into today's stuff. So what's the Central Limit Theorem actually say? Well, let's go ahead and read through the whole thing first, and then we'll break down what each part of it means. So first off, it says, if one of these two things are true, that the sample size of the sampling distribution is 30 or larger, or if the original data for the sampling distribution was already normally distributed, then you know that A, the sampling distribution is also approximately normal. B, the mean of the sampling distribution is equal to the mean of the original data. And C, and last, is that the standard deviation of the sampling distribution is actually the original data standard deviation divided by the square root of the sample size you used in your sampling distribution. Since that was a lot, let's go ahead and break down what each part of that means. Starting off with the two things that one of them must be true for us to use the Central Limit Theorem. The first one is the fact that your sample size must be 30 or larger. What do we mean by the sample size? Well, remember the sampling distribution is actually when you just are drawing samples from a population over and over. In this case, for my last video, we were drawing samples of 5. That would not be large enough for us to use for the Central Limit Theorem. But if I were to increase that sample size, so maybe I took 50 Larrys each time in that example and then recorded the mean, that sample size of 50 would be higher than 30. So then we would be able to apply the Central Limit Theorem. Now, the second item is actually that the original data was already normally distributed. If the original data was already a bell-shaped curve with the mean in the middle, symmetric on both sides, then you actually don't have to worry about that sample size of 30. As long as it was already normal, then we can go ahead and move on with our Central Limit Theorem. And what is it that we actually get? Well, the first thing is that your sampling distribution will be normal. So if you are taking a sample size of 30 or larger, or if it was already normal, then the sampling distribution itself is also going to be normal. Or if it wasn't before, it will now be normal. Meaning that we will now have a distribution that will be bell-shaped with the mean in the middle, symmetric on both sides, no matter what we were looking at before, as long as one of those two conditions were true. The second thing it says is that the mean of this sampling distribution is actually equal to the original mean. So if you found the mean of all of your data of the whole population before, that's actually going to be the mean of the sampling distribution as well. And the last item is that the standard deviation, which we mentioned in the last video will be getting smaller, will actually be getting smaller by an exact amount. We would estimate that the new standard deviation is going to be the old standard deviation divided by the square root of that sample size. So if you have a sample size of 100, then you just take the old standard deviation and divide it by the square root of 100 to get your new standard deviation for the sampling distribution. Mr. Caproni, were you just going to gloss over that crazy new notation you used for the sampling distribution? No, I can actually explain that now. So if you notice, I put those two symbols back on the screen. On the left-hand side, you'll see a familiar symbol, the mu, which stands for the mean of a population. And on the right-hand side, you'll see that lowercase sigma that we use to represent the standard deviation of a population. And if you remember, we also use X bar as a symbol for the sample mean. So when we're actually talking about this, that first symbol where it has the mu and then the small X bar is literally saying that this is the mean of all of your sample means, which is what a sampling distribution mean would be, because you collect a whole bunch of sample means and then you find the mean of those means. And that can be a little overwhelming. It's literally the mean of the means. So that's why they use that symbol. It's the mean of a population of the individual sample means. And it goes the same with the standard deviation symbol. It's the standard deviation of those sample means that we collected for our sampling distribution. Okay, notation aside, you said this was extremely important, and I don't really see any importance in it after we read through that. Well, then why don't you let me enlighten you? If you check out one of my old videos on normal probability distributions, you'd know that when we have a normal curve, we can actually make some amazing estimates about populations as a whole. We can find out what percent of the population wears a certain shoe size, or what percent of the population has a score above this, or what percent of the population wears this size of clothing. Those are all extremely powerful statements for a company to make predictions about what they're going to do in the future. That's why the central limit theorem is so important, because we are now taking ugly distributions and making them normal. You see, before we were using the normal curve to make these predictions about the population, but we were assuming that the data was originally normal to begin with. Well, guess what? That's not always the case. Sometimes it's ugly, sometimes it's lumpy, sometimes it's skewed right or skewed left. By using the central limit theorem, we can actually take ugly distributions from our original data and create them in a new way through sampling distribution where they become a normal curve. Now, all of those tools we used before for estimating things about the whole population, we can use them again by the central limit theorem. So now let's talk about applying the central limit theorem. Now remember, once we have the normal curve, we use something like geogebra.org or your calculator to find those probabilities about the whole population, or what percent of the population fell in a certain range. But the problem is that that technology, geogebra.org or your calculator or whatever spreadsheet you're using, it did require some information from us. First off, it needed to know that the distribution we're plugging in was normal. Well, the central limit theorem tells us that our data is going to be normal now from the sampling distribution. Next off, it needs to know our mean and standard deviation. So we're going to walk through an example to make sure you know what the mean and standard deviation of your sampling distribution is based off the information we gathered from our central limit theorem. So here's the example we're going to work with today. It says, when looking at data of high schoolers' GPAs across the US last year, the mean was 2.4 with a standard deviation of 0.8. If I took samples of 100 students at a time for my sampling distribution, what would I expect the mean and standard deviation of that sampling distribution to be? Well, remember, the central limit theorem said that the mean of our sampling distribution is actually just whatever the mean of our original data was. So that will still be 2.4. Next off, it said that the standard deviation is going to be the original standard deviation divided by the square root of your sample size, which in this case was 100. So you can see here, I showed the work, we got 0.8 divided by the square root of 100, and that gives you 0.08, which means when we're plugging our information into our technology, we would say that the mean is 2.4 and that the standard deviation is 0.08. Now our data is normal from the sampling distribution, and we have the correct mean and standard deviation to go along with that new distribution. Now the technology can shoot out the information we need about predictions for the population. Do you know what time it is? Time for you to hit that like button to let me know you learned something new, because we've reached the end of this video. We covered everything to do with the central limit theorem. We walked through what it says, we broke it down and talked about what each of those things meant, And we talked about how we would apply it by using technology and even worked through an example of where we would get that information for the technology. So I hope you learned something new today. If you did, like I said, go ahead and hit the like button below to let me know. Also, if you want to keep getting videos like this, go ahead and click the subscribe button as well, and you can see the new videos I'm releasing each and every week. I also do a whole series on ACT prep, so feel free to join me there as well. Well, guys, that's going to make it a wrap for today. So as always, thanks for joining me. This has been Probability and Statistics.